Hello everyone. In this class, we will talk about the NMR TR, repetition time. TR is actually a very important parameter for both NMR imaging and the relaxation analysis. And the TR setting is very important. Within MRI, there is T1 weighted, T2 weighted, and proton density weighted imaging. Weighted imaging is all related to the TR setting. In relaxation analysis, we also need to set the appropriate TR value when testing T1 relaxation time and T2 relaxation time or T2 mapping. So let's start by understanding the basic concept of TR. The repetition time TR is the time from the application of an excitation pulse to the application of the next pulse. It determines how much longitudinal magnetization recovers between each pulse. Okay, let's go with a hard pulse FID sequence. In this sequence, mm, TR equals to the P1, the pulse width, plus ACQ, the sampling time, and plus the TW, the waiting time after sampling. This is TR. After the sample is placed into the coil, a longitudinal magnetization vector is generated that is constant. We then apply a 90-degree RF pulse, and after the 90-degree pulse, the value of the longitudinal magnetization vector MZ it recovers it recovered as different by waiting for the different TR times. The waiting time TR determines the size of the longitudinal magnetization vector for the second applied pulse. We draw a diagram. This represents the TR time, and this represent the longitudinal magnetization vector MZ, and this 0 point corresponds to the point in time when the pulse is applied. When we set the TR to 100 milliseconds, a part of the longitudinal magnetization vector is recovered. And then we set the 300 milliseconds, more is recovered. And further on, more is recovered. Eventually, when TR is long enough, it will recover to the original longitudinal magnetization vector size. For example, to the initial state. This is artificially adjustable. After we place the sample, we form our initial longitudinal magnetization vector M0. At this point, the longitudinal magnetization vector is maximum. Mz equals to M0. When we apply a 90-degree RF pulse, which deflects the magnetization vector by 90 degrees, and at the end of the pulse, we sample the signal to obtain a maximum NMR signal. We then wait for the TR time. If the TR time is long enough, say TR equals to 10 seconds. By this time, the longitudinal magnetization vector has recovered from 0 to its initial state, at which point Mz equals to M0. For example, the longitudinal magnetization vector is the same size at this time as it was before the first pulse was applied. Then we apply a second 90-degree pulse. The magnetization vector is also deflected by 90 degrees, and the signal sample is the same size as the first one. After the third excitation pulse, the detected signal is still the same. So only if the TR is long enough, the signal acquired is the same each time. Let's look at the recovery process of the long TR corresponding to the the magnetization vector. This is the longitudinal magnetization vector before the first 90-degree pulse is applied. After this 90-degree pulse, the longitudinal magnetization vector is deflected by 90 degrees, and the mz at this point is 0. The length of the TR determines how much mz is recovered, and mz is recovered exponentially. Here, there is a concept of T1 relaxation time, which will be covered in the subsequent course. The T1 relaxation time is related to the magnetic field strength and the characteristic of the sample itself. Generally, if TR is taken to be 1 times T1 or more, MZ will essentially recover to M0. At this point, we apply a second 90-degree pulse and get the same signal at the first applied 90-degree pulse. Then wait for the third pulse of TR time, and the corresponding situation is still the same. This means that only if the TR is long enough, the NMR signal obtained after each applied 90-degree pulse is the same. Then we will look at the case of the short TR. The case of the first applied 90-degree pulse is the same as the one presented earlier. Usually after we put the sample, there is some preparation time. And this time is usually enough for the sample to produce the initial magnetization longitudinal vector M0. So the maximum signal is obtained after the first time 90-degree pulse. Then we will wait for the TR time, and this time we set the TR to be shorter. For example, TR equals to 300 milliseconds. After waiting for TR time, the longitudinal magnetization vector is only partially recovered. At this point, MZ is smaller than M0, which means that the sample has not yet recovered to its initial state. At this time, we applied a second 90-degree pulse. The MZ magnetization vector is also deflected by 90 degrees. And the signal obtained by sampling will be smaller than the signal after the first pulse. Waiting for TR time again, the third pulse. The situation is similar. MZ is smaller than M0. After several pulses, MZ will reach a stable value, but MZ will always be smaller than M0, which means that the signal strength collected after the subsequent 90-degree pulses will always be smaller than the signal collected after the first pulse. Therefore, we can compare the signal strength collected after the first pulse with the signal strength of the subsequent pulse to obtain the most suitable TR value for the sample. We will show you an experiment later. We also look at the recovery process of the longitudinal magnetization vector corresponding to the short TR. Before the first 90-degree pulse, the longitudinal magnetization vector of the sample is the maximum M0. After the 90-degree pulse, the longitudinal magnetization vector is deflected by 90 degrees. After the pulse is turned off, the longitudinal magnetization vector recovers from zero. If the TR is long enough, it can eventually recover to the initial state, which was mentioned earlier. But when the TR is short, the longitudinal magnetization vector mz is smaller than m0. At this time, when a 90-degree RF pulse is applied, the sampled NMR signal is smaller compared to the first time 90-degree pulse. Okay, so that's all for the course. We will show the video of the experiment later. Thank you.